This is slide number 51 and I am your presenter Asloob Mudassar. Types of lenses. You see that here we have shown 6 types of lenses that will be commonly used as a single lens. So double convex lens, you can see that radii of curvature are given and with their sign convention. Then plano convex lens, and the second you know that is the surface which is infinite in the radius. The third is a positive meniscus lens. You can notice the radii of curvature both are positive and R2 is greater than R1. Then we have a double concave lens. R1 is less than 0 and R2 is greater than 0. And plano concave lens, R1 is less than 0, R2 is again equal to infinity as in the above case. Negative meniscus lens, R1 is greater than 0, R2 is also greater than 0, but you know that here R1 is greater than R2, whereas in the previous case, which was a positive meniscus case, R2 was greater than R1. So you see that converging lenses are thicker in the center, whereas diverging lenses are thicker at the edges. All converging lenses have a positive focal length and all diverging lenses have negative focal length. The thin lens phase transmittance function from equation number 15 is reproduced over here. TL of x comma y is equal to e to the power minus iota k over 2f multiplied by x square plus y square. This is the phase transmittance of the lens. Is applicable to any of the above lenses if f is chosen according to the following equation. That is 1 of f is equal to n minus 1, where n is the refractive index of the lens material, and within the parenthesis we have 1 over r1 minus 1 over r2. So if you choose f according to the sign conventions given over here for any lens, then you can plug in that lens, that the focal length of that lens over here in the formula, and whether f is positive or negative, and you can use this phase transmittance of the lens. The radii of curvature are indicated in each case. In each case of the above lens, we have indicated the radii of curvature with their sign convention. Now about the spherical wave. Consider a spherical wave of radius, consider a spherical wave of profile a over r multiplied by e to the power minus iota k r, where r is given by r is equal to x square plus y square plus z square. The square root of all these quantities is equal to, if you take z outside the square root, you have within the square root as 1 plus x square over y square over z square. So you see that the square root can be expanded binomially, and we have z within the parenthesis we have 1 plus x square plus y square over 2z square plus and so on, because we are not interested in the higher terms. So if you replace here z by the focal length of the lens, you will have the quantities, that is r will be equal to approximately equal to z plus x square plus y square over 2z will be equal to f plus x square plus y square over 2f as in equation number 17. Under the quadratic approximation applied to its binomial series expansion. So you see that we have written equation number 17 under the binomial series expansion applied to the formula, which is r is equal to square root of x square plus y square plus z square. And you know that this is r which is appearing in the profile of the spherical wave, which and also in the denominator of the amplitude, that is a over r multiplied by e to the power minus k minus iota k r. This in other words means that a paraxial approximation to the spherical wave has been applied, or a small portion of the spherical wave front around the optic axis has been considered. So you see that we are considering a small region around the optic axis, that is we are considering the region under the paraxial approximation, or we are considering the region under the isoplanetic region. So it means that the spherical profile that is given by a over r e to the power minus iota k r under the expansion of r under the binomial expansion as given in equation number 17, we are actually considering the paraxial, or the region of the spherical wave around the optic axis, a small region which we call the paraxial region. So we are considering a small region of the spherical wave under the use of equation number 17. Spherical wave of profile of a converging wave can be written as spherical wave of profile is equal to a over r e to the power minus k r, and here we are substituting the value of r that we have calculated in equation number 17. So a over f plus x square plus y square over 2f, and similarly we are using the value of r in the exponent also, that is e to the power minus iota k, and r is replaced by f plus x square plus y square over 2f. And we can expand this one in the denominator, that is in the amplitude we have f plus x square plus y square over 2f. Since f is a very large quantity, we can ignore the x square plus y square over 2f in comparison with f, and we can approximately write the amplitude as a over f. Now we can expand the exponent as e to the power minus iota kf, which we have separately written, and the other quadratic phase factor has been separately written as e to the power minus k or minus iota k over 2f into x square plus y square. So we can drop the constant amplitude and we can also drop the constant phase factor, and you know that we can approximately write the spherical wave profile of the spherical wave as e to the power minus iota k over 2f. Within the parenthesis we have x square plus y square for the spherically converging wavefront, and this is given in equation number 18. Constant amplitude term and constant phase terms have been dropped. Spherical wave profile of a diverging wave can be written by changing or by replacing f by minus f. So in equation number 18 we are replacing f by minus f to get the wave profile of the spherically diverging wavefront, which is e to the power plus iota k over 2f. Within the parenthesis we have x square plus y square. This diverging wave profile is obtained at a distance equal to f from a point source. Let us pass this profile through a biconvex lens of a focal length equal to f. So you see that this profile that we have written for the diverging spherical wave is actually originating from a point source which is located at a distance f from the profile that we have listed. Now applying equation number 16 when a diverging spherical wave is incident on a lens. So you see that I have given here on the left hand side I have the field after the lens, and that is equal to the phase transmittance of the lens multiplying to the input field, which is ul of x comma y. So if you put the input field as the diverging wavefront that we have listed above, so you see that these two factors will cancel out each other exactly. Output, what will be the output? You know that then we get equal to 1 the product because the exponentials will cancel and we shall get only 1 over here. So the output is a plane wave. 1 means that the output is a plane wave of a unit amplitude normally to the z-axis. So due to being normal to the z-axis, the constant phase factor with the plane wave can be dropped and the unit amplitude only can be written, which we have done over here. Spherical wave profile of a converging wave. So spherical wave profile of a converging wave in the form of the input field incident on the lens can be written as ul of x comma y is equal to e to the power minus iota k over 2f. Within parentheses we have x square plus y square. Let's make this wave incident on the lens to find the field after the lens. So we are using the same formula, that is ul prime is the field after the lens, and on the right hand side we have ul, which is the field incident on the lens, and between them we have the phase transmittance function of the lens. So putting the value of input field for the converging lens as e to the power, before that we used as a diverging lens, now we are using the profile as a converging spherical wavefront as e to the power minus iota k over 2f. Within the parentheses we have x square plus y square. So solving this one, we are getting at the end that the output field will be e to the power minus iota k over 2, and within the bracket we have f by 2 and multiplied in the numerator by the parenthesis containing x square plus y square. So you see that here we have f by 2 rather than f, which means that the output is a spherically converging wave focusing to a distance equal to f by 2 on the z axis after the lens. Now Fourier transform generation with converging lenses. When we say that a field is incident on a thin lens, it means that it is incident on the first tangent plane of the lens, tangent plane to the left surface of the lens, and the field after the lens will be the field at the second tangent plane, that is the tangent plane to the right surface of the lens. So secondly, fields are monochromatic and coherent, forming an optical system which is linear in complex amplitude. Fourier transform plane is located at the back focal plane of a thin biconvex lens when the incident plane wave is a plane wave. So you see that when the incident plane is a plane wave, the focal length of the lens will be at its back focal plane, that is at a distance f behind the lens. Fourier transform plane can be located within the focal length distance or away or beyond it if the incident beam on a thin biconvex lens is spherically converging or spherically diverging. So for a spherical converging, as we have seen in this case over here, that if we illuminate the lens with a spherical converging wavefront, then you know that the light will be focused before the lens, before the back focal plane of the lens, and you know that in this case it was focused to a distance f by 2 rather than the focal length f at which the Fourier transform, at which the back focal plane of the lens exists. So we can shift depending upon whether we are using the converging wavefront or a diverging wavefront as the input field to the lens. Fourier transforming the properties of the thin lens when the input object transparencies through which the light passes are placed at different locations will be investigated. So you see that there could be many possibilities when we place an input object around the lens, that is, it could be just before the lens, it could be well away from the lens, that is well away behind the lens, or it could be just after the lens, or it could be well away behind, well after the lens. So you see that there are many possibilities. We shall discuss these possibilities for the lenses, and we shall calculate the field. Transparencies can be placed in front of a thin lens or behind a thin lens or at the front focal plane of a thin lens. These three cases are the special cases of interest, and we shall discuss them. So now we are going to discuss the first case, which is the input just before the lens. That is, the input is just touching the lens, you can say. A biconvex lens of a focal length f and the input object in transmission mode are lying on the xy plane. That is, the lens and the object both are located at the xy plane, and the optic axis of the system is along the z direction. Amplitude transmittance of the object is represented by t subscripted a as a function of x, y. So this is the amplitude transmittance of the object that we are using just before the lens. A plane wave of amplitude A is normally incident on the object, so we can ignore its phase, its constant phase. Ignoring the constant phase factor due to the plane wave, the field just after the object, after the object represented by UL of x, y is given as. So you see that the field just after the object is UL of x, y is equal to A into TA of x, y. So you see that this field on the left hand side is the field just after the object, or you can say this is the field just before the lens, or this is the field incident on the lens. So in equation number 9, on the left hand side you have the field which is just incident on the lens. The field just after the lens represented by UL prime of x, y is given by. So the field just after the lens will be equal to the phase transformation factor of the lens multiplying to the input field on the lens, which is UL of x, y as given in equation number 20. So you see that here the input field is of infinite extent. The lens is also of infinite extent, because there are no factors which are limiting the sizes of these fields or the field of the size of the lens. To limit the size of the lens, we use and define a pupil function p of xy, which may take the shape of a circular, square or rectangular aperture. Circ function or the circular function, abbreviated as a circ, will be more appropriate to specify the circular aperture of the lens. So let's case the general case of the pupil function, which is p of xy is equal to 1 within the lens. So it means that the lens will be act as a clear aperture for this pupil and 0 outside, and the lens will be surrounded by opaque region outside this region, that is outside the lens region region the lens will be opaque, no light will pass through the region outside the lens, but only the light will pass through the lens, and the light will not be attenuated because the pupil function has a transmittance equal to 1 as given in equation number 21. So you see that on the figure we have shown some essential parameters of our optical system that we have described above. So you see that the optical axis is along the z axis and is passing through the center of the lens and also to the center of the input object, and also to the center of the output plane. The input plane is xy plane at which the input object exists, and also the lens also exists at the same plane because the lens is a very thin lens. So both are coinciding with each other, and you know that there is a difference between the two planes, that is xy plane and the uv plane are parallel to each other and separated by the focal length of the lens equal to f. So uv over output plane, so or we may regard it as the Fourier plane because it is located at the back focal plane. So rest of the things are very clear, you know that. So a more accurate form of equation number 20 is obtained by multiplying the right hand side of equation 20 by the pupil function. So you know that in equation number 20 we can now multiply the pupil function as given in equation number 22. So you see that in equation number 20 we have included only the pupil function. So you know that this pupil function now limits the size of the input fields, or you can say it also limits the size of the lens aperture. To find the field to the right side after a distance z is equal to f, we use the Fresnel diffraction formula. So you see that we have the field just after the lens, which is given by equation number 20. Now you see that we want this field to be propagated to the UV plane, which is at a distance f. So we need to use the Fresnel diffraction formula for that one, with capital Z is equal to f. So this is the diffraction formula that we have written, and UF is the field at the Fourier plane, which we have referred to as f, and there the space coordinates are u, v, and you know that we have these phase vectors that appear in the formula of the Fresnel diffraction formula, and we have the double integral, and you know that this UL prime of xy is the field just after the lens and multiplied by the quadratic phase vector. You know that in the Fresnel we have two quadratic phase vector. One is quadratic phase vector containing u square plus v square. This is the phase vector associated with the output plane, and we have another phase vector within the curly bracket within the integral, which is e to the power iota k over 2f multiplied by x square plus y square. This quadratic phase vector is associated with the input plane. And you know that UL prime of xy is the field just after the lens, and the rest of the parameter, which is e to the power minus iota 2 pi, within the bracket we have fu multiplied by x plus fv multiplied by y and integrated with respect to dx and dy. These are the parameters of the Fresnel integral as given in equation number 23. And you know that in equation number 23, in the exponent form especially, we have fu and fv are the Fourier variables at the Fourier plane, where the space variables are u, v. So fu and fv are the Fourier variables, and we can also define the space variables at that plane as uv variables, and these two variables are connected by equation number 24. So fu, fv is equal to u over lambda f is equal to v over lambda f. So you see that this is the connection between the Fourier frequencies and their corresponding space variables as given in equation number 24. And you know that in equation number 23 on the left hand side we have the space variables. Once we have evaluated the integrals, you know that the integral would contain fu and fv, and those fu and fv should be replaced by equation number 24, so that we have the right hand side depending only on the parameters u and v, so that we can have the right dependence. So the left hand side is a space dependent quantity and the right hand side should also be a space dependent quantity. So you know that in equation number 25 we have replaced fu and fv in equation number 23 by their values which are shown in equation number 24. So the formula in equation number, revised formula in equation number 25 is listed, which is field at the Fourier plane or at the back focal plane of the lens represented by small f as a function of uv is equal to this one that we have written. Just the difference is that we have replaced fu by u over lambda f and fv by v over lambda f. So using ul prime of x comma y from equation number 22 and setting the pupil function to unity, we obtain the result from equation number 25 as given. So you see that now this is the field which is in the curly bracket within the equation number 25 within the integral, that is ul prime of x comma y. This was the field just after the lens. Now we connect this field with the field which was incident on the lens. And you know that this is what we have done in equation number 26, that is we have replaced that field by the pupil function of the lens and by the input field which is ul of x comma y. And you know that with this field there was another quadratic factor that you can see from equation number 22. This one, this quadratic factor is to power e to the power minus iota k over 2f within the bracket x square plus y square. So this quadratic factor, so you can see that in the formula that we are discussing right now, that is a pupil function and ul of prime is present, and this phase factor which is the quadratic phase factor in x square plus y square will cancel out the quadratic factor which is present in this curly bracket in equation number 5. So due to negative sign in equation number 22, so this you know that quadratic factor within the curly bracket in equation number 25 will be cancelled out, and we have the formula in equation number 26. So equation number 6 can be written in the following form. If we ignore you know that the pupil function, we can set the pupil function equal to 1, and we can write apart from these complex quantities, we have the equation in the equation number 26, the integral in the in equation number 26. You know that this is nothing but the Fourier transform of the field ul of x comma y, which can symbolically be written as in equation number 27. So we have written that using the Fourier operator operating on ul of x comma y and evaluated at fu is equal to u over lambda f, and fv will be evaluated by at v over lambda f. So you see that equation number 27 will give you the symbolic form of the field at the back focal plane of the lens, whereas the analytical form or the explicit form will be given by equation number 26. And you know that this integral is very important, which is the integral that gives you the Fourier transform of the field ul of xy, which is the field just behind the lens. So this is the Fourier transform of the field just behind the lens, and which we have written symbolically in equation number 27. So this states that the field at the back focal plane of a converging lens is the Fourier transform of the field just before the lens multiplied by the quadratic phase factor at the Fourier plane, a constant phase factor and the scaling factor. So you see that there are some scaling factor and the constant quadratic phase factor which contains u square plus v square, and the scaling factor is lambda f, for example, in the denominator. These are present you know that in equation number 27. We can recognize the equation number 27 as the Fraunhofer diffraction formula. We thus conclude that the field at the back focal plane of a converging lens is the Fraunhofer diffraction formula of the field incident on the lens. So you know that by using a lens we can generate the Fraunhofer diffraction formula at its back focal plane. The more accurate approach is to replace the pupil function p of xy, which we have set equal to 1 in equation number 27, with the circ function circ of r over r naught, that is the circular function of radius r naught, where r naught is the radius of the lens aperture. Thus equation number 26 can be rewritten as. So you know that we have written the equation number 26, but here we have incorporated the circ function circ of r over r naught as in equation number 28. So you know that this integral is what? This is the Fourier transform integral as we have simply represented in equation number 27. So similarly, the term in the curly bracket, this integral gives you the Fourier transform of the term in the curly bracket. So that's why we have used the operator in the operating on the terms in the curly bracket, and of course after the Fourier transform, these will be evaluated at fu is equal to u over lambda f, and fv will be evaluated at v over lambda f. Now you know that we have given that is the Fourier transform of one quantity, that is the Fourier transform of the circ function will be convolved with the Fourier transform of the input field, which is ul of x comma y. We have applied the convolution theorem to the second step in equation number 29. And you know that rather we have with the circ function, we have rather than representing the tau as the Fourier operator, we have used b as the Fourier operator, which stands for the Bessel Fourier transform, because for the circularly symmetric object we transform the linear Fourier operator into the Bessel Fourier operator. So b operating at curly bracket is the Bessel Fourier transform evaluated at rho, because rho is equal to s over lambda f, which we shall be explaining with greater detail next from our earlier knowledge on Bessel Fourier transform. Because you know that rho will be a operator, rho will be the Fourier frequency, Fourier variable at the Fourier variable associated with the polar coordinates, and you know that s is the space variable associated with the polar coordinates. So rho will be equal to fu square plus square root of fu square plus fv square, and we can write this is rho we have written in terms of the quantities which are Cartesian, you know that, and then you know that we have replaced these with their scaling factors, that is fu will be replaced by u over lambda f, and fv will be replaced by v over lambda f, and then finally we have 1 over lambda f multiplied by the square root of u square plus v square, and this u square plus v square, the square root of this quantity is represented by s, because you know that s is a space variable in polar coordinate system. So now let's evaluate the Bessel Fourier transform of the circ function, which we have already evaluated earlier many times, and then you know that it is the Bessel function, it is the j1 of 2 pi r naught rho divided by r naught rho, evaluated at rho is equal to s over lambda f is equal to mu is equal to square root of a mu square plus a v square divided by lambda f. So you know that we are replacing rho by this quantity in the second row, and then we are rearranging this term, because we can identify this term is nothing but a Jing function, because we have 2 pi over there, and the numerator and the denominator in the j1 as the argument are the same, because except 2 pi factor. So we can write it as Jing of r naught multiplied by u square plus square root of u square plus v square divided by lambda f. This is in equation number 30, which gives the Fourier transform of the circ function. Now you know that we can in equation number 9 the Fourier transform, the Bessel Fourier transform of the circ function is known, and we have also evaluated at rho is equal to s over lambda f. So using equation 30 in equation number 9 we have this. So you see that we have replaced the Bessel Fourier transform by the Jing function, which we have evaluated, which is the Fourier transform of the Bessel function of the circ function, as in equation number 31. So let's rewrite equation number 31, that we can move Jing function to the leftmost side of the equality, and then we can write down all other quantities on the right hand side of the convolution sign. So what these quantities are? These are what we have written in the third term as identify these one, that is the Fraunhofer field due to the field incident on an infinite sized lens aperture. So after the convolution we have the quantities which are the Fraunhofer field due to the field incident on an infinite size lens aperture. So the field at the back focal plane of the lens is equal to the Jing function convolving with the Fraunhofer field due to the field incident on an infinite sized lens aperture. So So it means that this Jing function will also limit due to the convolution. It will limit the size of it will convert the infinite size field to the finite size. So in equation number 32 we have calculated the field, but you know that the intensity is a physically measurable quantity. The intensity at the back focal plane or the Fourier plane is referred to as the energy spectrum, but if it also depends upon the time variable, it will be referred to as the power spectrum. The expression for the intensity using UF of U comma V from equation number 20c is given below. So we have written, you know, that the intensity expression is equal to UF multiplied by its complex conjugate. So having done that one and multiplying or that one on the second parameter on the first row in equation number 32, we are writing the expression that the output field as a function of uv, that is at the output field, is equal to 1 over lambda square plus f square, and you know that here we have taken the absolute square of the integral. And you know that other exponential terms which were present in the Fraunhofer field has been eliminated due to being we are considering the intensity. No complex variable is now present in equation number 33. So we can represent the UL field in terms of the object transmittance, and you know that in terms of the object transmittance was equal to A times TA. So A was taken outside, which becomes A square, and then you know that we have TA, which is the amplitude transmittance of the input object, which was illuminated by a unit amplitude plane wave. So you know that we have now TA of x comma y, and this A on the left hand side, which is A square, now it is actually the amplitude of the unit amplitude plane wave, which is not the unit amplitude but the plane wave with the amplitude equal to A, normally incident on the object having a amplitude transmittance TA of x comma y as in equation number 34. This is the output intensity at the back focal plane of a biconvex lens having a focal length f when an input object with amplitude transmittance t of x comma y is placed just before the lens and illuminated by normally incident plane wave of amplitude equal to a and wavelength equal to lambda. So you see that we have calculated the amplitude and the intensity of the field at the back focal plane of the lens when the input was just placed just before the lens. So one case has been solved. So this is the end of slide number 51.